Hello everyone, this is Professor Deepika from Department of Electrical and Electronics Engineering of Sai Vidya Institute of Technology. In the last video, we were discussing about some of the numericals related to the specific energy consumption, specific energy output, and also the mechanics of train movements of electric tractions. So in today's video, we are going to study about what kind of motors will be preferably used for the train movement or will be used in the traction system. So that we are going to study because motor is the one which is providing the motive power for the moment of the electric traction. And we have different kinds of motor. Actually, we have DC motors, and in the DC motors also we have DC series motor, DC shunt motor, DC compound motor, and also we have single phase motors, that is we have induction motors. So and also in the three phase we have again three phase induction motor. So now we will study what kind of motors will be used in the traction system. So first, before going to the specific type of motor, we have to know what is actually the features with respect to the motors that we are going to consider. So here we are generally considering the two features, that is, one is the mechanical feature and the other one is called electric feature. So first we will discuss about the mechanical feature. So coming to the mechanical feature, first one, the motor should be robust and capable to withstand the continuous vibration, because it will be of long run usage. So therefore the motor should be of robust construction, that is, it should be very hard and very good construction, and also it should be capable of withstanding continuous vibrations, because the traction system will be always used in the always used, or it will be continuously used, hence it should withstand the continuous vibration. So that is one of the mechanical feature. And weight should be minimum, because the motors are installed beneath the train system. So therefore its weight should be minimum, okay, because the overall traction system weight should be less, hence the weight should be minimum with respect to the motor. And also it should be smaller in overall dimension as well as in the diameter, again as it is installed beneath the traction system. And it should be of totally enclosed type, because why, because there will be a dust or water content or any dirt will be accumulated over the motor. So we have to avoid that. If there is any water content and all, there may be a possibility of electric shocks and something and all will happen. So therefore it should be totally enclosed type, because it should be protected from the dirt or dust or any kind of water content. So that is one of the thing. Next, it is usually made by cast steel or fabricated steel, because the steel has enough strength to withstand the payload capacity. Hence, it is made of usually cast steel or fabricated steel. So these are the some of the mechanical conditions or features we are going to consider while we are selecting the motors for the traction system. So next we have electric characteristics. So coming to the electrical characteristics, first and foremost thing is it should have high starting torque, because the motor usually will be motor usually we or the traction system what we have, it is usually under rest condition, and when we accelerate it, then it is going to move, correct. So while it is moving, it has to overcome the inertia force, correct. So therefore, and also the weight on the traction system will be very more, because there will be a passenger weight and there will be a whole system weight. So it should be capable of withstanding all the weight, and it has to move on. Hence the motor should provide high starting torque and simple speed control, because usually the traction systems also will be used in the suburban and urban railway system. In the suburban and urban, we got to know that there will be a more often or there will be a frequent stops will be there. That means the distance between the two stations will be very less. Hence, it should produce simple speed control. Next, it should have self-relieving property. That means what? The speed torque characteristics of motor should be such that speed may fall with the increase in the load. So this is one of the important property, electrical characteristics with respect to a motor. That means what? If the load is increasing, then the speed should reduce. If load increases, then speed also increases, then that is not a good kind of motor. And therefore, we call it as a self-relieving property, because if load is increasing, if the speed is going to reduce, then we can actually control the traction system. Hence, the speed torque characteristics with respect to the traction system should be in this way. That is, speed should reduce with increase in the load or torque. So next we have that is, motor should be self-protective against excessive overloading, as power output of a motor is proportional to the product of torque and speed. As I told you, speed is, if the torque is increasing and the speed, that is, if the load is increasing, then the speed should reduce. So that is called as self-relieving property. So therefore, motor should also be protect from the overload conditions or overload condition, because the power output, what we are calling, so that is actually proportional to the torque and speed. Hence, the power output may also increases. So therefore, it should be protected against the overload condition. This possibility of dynamic or regenerative braking. That is, if we want to make a train to come to a rest position, then we are going to apply the braking system. So in the braking system, again, we have rheostatic braking, dynamic braking, and the regenerative braking. So the rheostatic braking will, usually we are going to avoid that. Why that is so, and all we are going to learn in the coming slides. Usually we are going to prefer the dynamic braking. The regenerative braking, if it is possible, then it is very good enough, because the power will be saved over here. Hence, there should be a possibility of dynamic or regenerative braking with respect to the motor. So these are the some of the electric characteristics, and we also have some of the other characteristics. That is, it should be capable of withstanding voltage fluctuations. So that means what? Usually the supply voltage will be fluctuating in nature. So therefore the motor should withstand this voltage fluctuation. So that is one of the main consideration. And coming to the, it should be capable of withstanding the temporary interruption of supply. That is, when there is a crossovers of insulators, there may be a possibility of cutting off the supply. There may be a possibility of interruption of supply. Hence, the motor should also withstand these type of condition. So next, overload capacity. So sometimes what happens, the overload may occur. So therefore, the motor should capable of withstanding this overload capacity. Next, coming to the parallel running, only one motor cannot run the traction system. So usually we are going to employ many number of motors to provide the motive power. So hence, when they are running in parallel, so that also you are going to study in the coming slides. That is, usually we are going to make the motors first in series, then in parallel, sometimes in parallel, then in series. So therefore, when these kind of combination usually we are going to do, during that condition, all motors should share the load equally. Okay, so that is nothing but the parallel running. That is, when the motors are running in when the all the motors are running, or when the motors are running in parallel condition, it should be that is, all motors should have a equal load, or they should share a equal amount of load. So that is nothing but the parallel running. And this is the obvious thing, that no motor will meet all the requirement mentioned above. That is, the motors what we are having, so all the motor will not meet these requirement. So usually we are going to consider some of the main important characteristics, and we are going to select the motors. Usually for the DC system, that is, if the supply is DC, and if you are preferring only the DC system, so in that case, usually series and compound motors will be used. And for the AC system, either we are going to single phase series motor or three phase induction motor. So these are the some of the motors we are going to use for the traction system. So next, coming to the operating characteristics of DC motor. So what are the operating characteristics? That is, before we are using the motor, we have to know what is actually the operating characteristics of the motors. Okay, so that is nothing but the performance characteristics. So performance and hence suitability of a DC motor is determined from its characteristics known as performance characteristics. That is, the performance and also its suitability of the DC motor will be determined from its characteristics. So that is nothing but the performance characteristics. First one, we have torque armature current characteristics. So that is, it is a curve between the torque developed and also with the armature current IA. And speed armature current characteristics, it is a curve between speed N and armature current IA. And coming to the speed torque characteristics, it is a curve between speed and the torque developed in the armature. And it is also called as mechanical characteristic because these two are the mechanical parameter. Hence, we also call this as mechanical characteristics. So these are the some of the three operating characteristics with respect to the DC motor. So these three are very, very important. By these parameters only, like by these characteristic only, we are going to judge which type of motor is suitable. So coming to the important relationship, we have three important type of relationship. One is the armature current relationship, and speed relationship, and also the torque relationship. So let's see one by one. First one is torque developed by DC motor. So coming to the torque developed by DC motor, where here TE is nothing but electromagnetic torque developed in Newton meter by the motor running at N RPS. That is, the torque developed inside the motor, we call it as TE. And the unit here it is Newton meter, and here it is running at N RPS, that is revolutions per second. So here we are going to consider the revolutions per second. And the power developed is nothing but what? Power is nothing but rate of work done, that is work done by second. And the power developed can also be written as torque into speed, correct? So we all know this, that is the product of torque and angular speed will also called as the power developed. So how can we write the angular speed? So angular speed will be written as 2 pi n, where n is nothing but speed in RPS. Remember, it is in RPS. So next, the electrical equivalent of mechanical power. You can see here. So this is nothing but the mechanical power, correct? Here we have written the equation in terms of mechanical power. If we want to convert this into electrical power, then how do we write this? So we know that power is nothing but voltage into current. So here the voltage at the output is nothing but the back EMF, and the current is nothing but the IA. Hence we have written as EBIA into watts. And at steady state condition and all, these two powers are equivalent, because this is the mechanical power we have written in terms of mechanical mean, and this is the mechanical power we have written in the electrical mean. So hence these two are equal. So let us equate these two equations. So next, what we can write, the TE is nothing but what? The torque developed is nothing but EBIA divided by 2 pi n. So remember, n is in RPS. If I want to convert n into later we can do that. Let us simplify this. 1 by 2 pi is nothing but 0.159 EBIA Newton meter. And if I want to convert the speed in RPS to a RPM, then I have to divide it by 60. Okay, so now I'll change the nomenclature as n by 60. So hence the equation again it become 2.55 EBIA by n Newton meter. So where n is in RPM. So next, substituting EB is equal to, so we know that back EMF formula that we have seen in the derivations of the motor in your lower sums. You have already studied the equation of back EMF, that is phi z NP divided by 60A. So this I'm going to substitute in the above equation, that is in the place of back EMF I'm going to substitute this equation. Hence the equation will become 9.55 5Z NP by 60A into IA by N, where N and N will get cancelled out. And here you all know that TE is nothing but torque, electromagnetic torque in Newton meter, and whereas phi is nothing but flux in Weber, Z is nothing but total number of armature conductors, and again N is nothing but speed in RPM, and again P is nothing but number of poles, and E is nothing but number of parallel paths, and IA is nothing but armature current. So here N and N will get cancelled, and we can write in this way. And you can observe over here, the electromagnetic torque what we are talking about. So this is directly proportional to the armature current. Please remember that the torque developed here, it is directly proportional to the armature current, because for a particular machine, these A term P and Z are constant. Hence we can see that the torque is directly proportional to phi into IA. So in case of DC motor, we know that flux is constant. So as flux is constant, torque is directly proportional to armature current. Hence we could write in this way, that is the straight line, that is the linear relationship. There is a linear relationship or linear direct relationship between torque and armature current, because torque is directly proportional to armature current. That is, if the armature current is increased by 2%, again the torque will also be increased by 2%. Hence, there is a straight relationship or the linear relationship with respect to the shunt motor. Okay, coming to the series motor, again the torque is again directly proportional to flux into IA. Hence the relationship again, it is directly proportional, but it is not a linear relationship. It is in this way. So this is nothing but a linear relationship. After some time, what happens? Flux also become as the core saturate, the flux also become constant. Hence, hereafter it will become a constant relationship. So this is nothing but the torque armature current characteristics. So please remember that the torque and armature current is directly proportional. A torque and armature current is directly proportional. So this is nothing but the torque and the armature current characteristics. So next we will talk about the relationship between speed and armature current. So for this, we know that the back EMF developed in a DC motor, it is nothing but the generated EMF, correct? So we can write the back EMF as one equation. We know that 5Z NP by 60A, and also we also know that the supply voltage what we are feeding, so that will be equals to the back EMF generated plus the drop in the armature, correct? That is V is nothing but EB plus IA into RA. Now how can I write EB? EB is nothing but V minus IA into RA. So we have this equation also. Now let us equate these two equations. So when I equate these two equations, now let us resolve for the speed N, because it is a speed and armature current characteristic. So now I'll take out only N, and the remaining terms are transferred to the RHS side. Hence we have this equation. And we know that for a particular machine, the number of parallel paths, number of poles, and the number of conductors are constant. So then how can I write? N is directly proportional to V minus IA into RA divided by phi, because for a particular machine, all these terms are constant. Then so then this is the thing. Then usually the armature drop what we are calling IARA, so this armature drop is usually negligible if or it is very small with respect to the supply voltage. Hence I can write in this way, because IARA is very small compared to the supply voltage. And you know that for a particular system the supply voltage will be constant, correct? So supply voltage will be constant. Hence what can I write? N is N is inversely proportional to the flux. So what I got to know here, N is inversely proportional to the phi if the supplied voltage is constant. So what you can observe over here is, so speed is inversely proportional to the flux. Again, flux is directly proportional to the armature current. So instead of flux, I can write IA also, correct? So in the DC shunt motor, what happened? The flux is constant, correct? Usually the flux is constant in the DC shunt motor. Hence, what I can say is speed is constant. That means if the current increases, also speed remains constant in the DC shunt motor. Hence, I can write the relationship like this. That is, if the armature current increases, but the speed is constant in case of DC shunt motor, because flux is constant in the DC shunt motor. And coming to the DC series motor, it is inversely proportional because here flux is not constant. Again, it is dependent on the armature current. You can see here it is inversely proportional. Inverse relationship is there. As armature current increases, the speed is going to reduce. And if the armature current reduces, then the speed will be more. Hence, at the starting, the speed will be more. And if you increase the armature current, then the speed is going to reduce. So this type of particular relationship we want for the traction motor. That is, if the armature current increases, then the speed should reduce. So this is one of the that is why we are going to prefer the DC series motor rather than the shunt motor. So next we have relationship between speed and torque. So coming to the relationship between speed and torque, the torque developed, that is TE, correct? So that is nothing but what phi we have got to know by the first relationship, that is 0.159 phi ZP into IA by A. So this is one of the equation we have. And now let us resolve for A by phi ZP. Let us retain only these terms, that is A by phi ZP, and remaining we can write it as 0.159 IA by T. And substituting the above equation in the equation, that is N is equals to V minus IA RA divided by phi Z into 60 A by P. Let us substitute A by phi ZP value here. Okay. So if I substitute A by phi ZP value, then the equation will become like this. And again, you know that all these things are constant. Let us write like this. And you can observe over here. And you can observe over here is speed and torque is inversely proportional. You can see here the speed is inversely proportional to the torque. That means what? If the torque is increasing, then the speed is going to reduce. Again, in the DC shunt motor, we got to know that speed is constant with respect to the armature current. Hence, the speed torque relationship for the speed torque relationship for the speed torque relationship for the DC shunt motor is constant, and for the series motor it is again in the inverse relationship. That is, if the torque is increasing, then the speed is going to reduce. If the torque is less, then the speed will be high. So this kind of thing we will be having in the series motor. Hence, usually the series motor is preferred. So in the next video, let us discuss about the problems with respect to the traction systems, with respect to these operating characteristics. Thanks for watching the video.